Okay. So the last concept is for this chapter, the last concept is going to be the concept of the binary stars. Okay. Hmm, come on. Concepts of binary stars. Okay. So binary star basically it consists of two stars moving around a common center. Okay. So this is the concept. This is the main concept of the binary stars. Okay. The concept or the whole concept for this binary star system is not in the part of the syllabus, but we just need to know what they are and how their gravitational force related with each other. Okay, so we can say that it is the system of two stars moving moving around a common center. Okay, and the second point is their gravitational force provides the centripetal force, okay, force to the stars, okay. And the third point is the gravitational force is equal, equal, and opposite with the gravitational, come on, with the gravitational force of the other star, okay, due to the Newton's third law, right? Due to the Newton third law. Okay, this is a concept now. So if they are in the circular motion or in the planetary motion around a common center with the same force, so their period of rotation is also going to be the same. Okay, the period of rotation for both the stars is going to be the same. Okay. So this is the main or the whole concept of the binary stars. Okay, the binary stars are basically the two stars moving around a common center. Okay, if I can show you the picture of the binary star, let me see. Binary star. I want the image, please. Okay, you can see this picture. It's not that much. If the save my exam did it, save my exam. No, we don't have it. Okay, so we can have anyone. Let's take this one. Okay, so this is the picture of the binary stars. Okay, so and it is like two. It is a two star, moving around a common center. The center will be somewhere here. Okay, and they're moving around it. Okay, so this is how it works, right? Now, if we try to relate the gravitational forces, so for one star, for one star, mm, for one star, we know that gravitational force Fg provides the centripetal force mr omega square. Okay, this is for one star. Okay, you can further expand it, and this is going to be gmm m over the I square is equals to mr omega square. Okay, but this is for one star. Okay, it seems like the Kepler's law thingy, but r cube omega squared, right? So you can use this relation to find the period of any one of the star. Okay, okay, and this r is going to be the separation between the two star. Actually, not the separation, but this point. Let's say okay, they're moving around a common center. The center is right here. Okay, this is a common center, right? So the distance from the center of one of the star to that point is, let's say, x. Okay, and let's say the whole distance between the two stars is, let's say, L. So can you guys tell me this distance, please? Yes, anybody?
L minus x.
Very good. L minus x. Good. And this is a common
Sir,
center.
uh, I was in same exams as one concept which is orbital radius,
Mm-hmm.
which is r is equals to small r is equals to capital R plus h. Is that like going
It is
going
the
to be asked a
same.
lot?
Uh, it is just a concept they've given the name. Okay, they're nothing to do with the like. It's a simple thing. They've just given the name. Okay, the orbital radius is going to be like, if you have the planet and this is the R. Okay, and let's say this is the orbital. Let's say this point is where something is moving. Okay, and this distance is h. Okay, so this distance is, let's say, h. Right, so you know that the orbital radius for the thing orbiting this radius is going to be just r plus h, right? So it's a simple concept. Yes, they ask you a lot about this thing, but in the numerical question, okay? So you just need to know how you have to add the heights above the surface of the planet with this with the radius if they're asking for the orbital velocity or anything relating it. Okay, clear?
Yeah.
Okay, so okay, so for this one, let's say, let me just consider x in place of r. Okay, and x cube in place of r, and I have this thing. And okay, this is the equation for one star. Okay, for the two stars, for sorry, for the two stars, we know that their gravitational forces, their resultant forces are equal. So we can say that m, sorry, m1, and then um, and then and then x omega square is equals to m2, and then L minus x, and then omega square, right? Well, like if you want to relate the two stars, so you can relate it with this formula. Okay, you can cancel the m and m out. Okay, and you'll be left with m1 over m2 is going to be L minus x divided by x. Okay, the ratio of the two mass given by L minus x over x. Okay, clear. And this in the first case where we have m1 and m2. Okay, so both the mass going to be the mass for the first one and the mass for the second one. Okay, I'm writing this mass as m1 and m2 to make more sense. M1 m2, and this is m2, and let's say m1 is for this mass, m2 is this mass. Okay, so these are this is the concept of the binary stars. Okay, as being the two star moving in a circular orbit, right? Now let's try some of the questions of the binary star, and then we are actually done with the gravitational field strength. Okay, and 20 September 2025, right? Now I also send you this workbook. Okay, it contain like the questions from 2002 till 24. Okay, so you can try the questions. Okay, I'm also giving you the marking key for this one, so that if you want to check with the marking key, you can check it. Where is your group? Yeah, documents, gravitational field. Okay, there you go. Okay. Do I send you the workbook, right? Book one. Yep. Okay, so just try the questions, guys. And okay, so if I consider we did the orbital speed, we also complete the concept of orbital speed. Yes. So this is a question. Okay, wait. So this is a question. Yes, and this is the question. Wait. It is from 2020. Yeah, this is okay. Yes. Okay, fine. So copy and paste. Just give me a second, please. Yep. Paste the pages. Okay, there you go. Can you please read the question? Anybody? If I you read the question.
Okay, which one? This?
Yes.
Okay. A binary star consists of two stars A and B that orbit one another, as illustrated in figure 1.1. The stars are in circular orbits with the center of both orbits at point P, a distance d from the center of star A. Explain why the centripetal force acting on both stars have the same magnitude.
Okay. We know that due to the Newton's third law, due to the Newton's third law, the force will going to be equal and opposite on both the stars, right? So that's why. Okay.
The,
So, hmm,
okay. Oh, I thought we had to read the next question.
wait. Newton's third law, the magnitude of the forces should be equal and opposite, equal in magnitude and opposite in direction. Okay, please move on.
The period of the orbit of the sun is about 4 years. Calculate the angular speed omega of the stars.
Okay, so omega is 2 pi.
Uh, yeah, 2 pi over t.
Very good. Okay, so 2 pi over, so t is 4 years. 4 into 1 year contains 365 days. 1 day contains 24 hours. 1 hour contains 60 minutes. 1 minute contains 60 seconds. Okay. How much?
4.98 into 10 to the power negative 8.
4.98 negative 8. Okay. Okay, please move on.
The separation of the centers of stars is 2.8 into 10 to the power 8 kilometers. The mass of star A is Ma. The mass of star B is Mb. The ratio Ma over Mb is equals to 3. Determine the distance d.
Okay. So you first have to relate the two things. Okay.
What is the distance d?
Let's The D
Uh,
is this one, okay, and the whole distance is 2.8 exponent 8 kilometers, which and you can find this distance as well, which will going to be um total, which is 2.8 exponent 8 kilometers minus D, right?
yeah.
And to relate that, we can equate the two masses, we can equate the two forces, okay? So we can say that centripetal force for both the stars is going to be same. Okay, so m r omega, sorry, m a and then x for its distance and omega squared for the first one should be equal to mb, and then d minus x, d minus, sorry, total distance, which is 2.8 exponent 8 minus d equals to and then omega square. Okay, and this is d, by the way, right? Omega and omega are constant for both the planets, so that's why they never collide with each other, right? Otherwise, if the omegas would be different, then they both end up colliding with each other, right? So ma over mb is going to be equal to 2.8 exponent 8, okay, minus d over t, right? they mentioned the ratio. Okay, so the ratio is basically mm, 3. Okay,
MA or
so
MB is equals to
yes,
3,
is
right?
3, right? So you can replace that with 3, and then if you bring the d here, so it is going to be 3d plus d equals to 2.8 exponent 8. Okay, and then 4d divided 4 d divided by that value. So d is going to be 2.8 exponent 8 divided by 4. Okay.
7 into 10 to the power 7.
Okay. 7.0 exponent 7. Perfect.
What's a unit?
Wait. The kilometer, okay? So we don't have to convert. Okay. Um, just a minute, please. Okay, this is the next part. Okay. Now, okay, please move on.
Use the answer in A2 and B1 to determine the mass MB of star B. Explain your working.
Hmm. So, okay, A2 and B1. Okay, A2 is this one and B. Okay. So we can relate the two things using the gravitational force. Okay. So gravitational force provides centripetal force. Okay.
Do we have to
So
write this?
yes, because they're saying explain your working, right? So in all the A2 questions where they ask you to explain your working, then you have to write any statement that explains the whole thing. Okay. Now just put in the value. So GMA MB over the distance of MA to the point which is D. Okay. D square is equals to MB and then D and then omega. Okay. So just cancel these things out, and GMA is basically equal to what? To determine the, actually, sorry, wait. So this should be B, this should be A. So this get cancelled out, and this is D squared, and then, okay, it's not D squared, it's basically this distance, D minus the whole thing. Let me just take R for it. Okay, and then um it will going to be R cube and then omega squared, right? Now,
What is R? It's a.
it is this distance, 2.8 exponent 8 minus D. Okay, so R
Okay.
is basically 2.8 exponent 8 minus D, which is 7 exponent 7. Okay, so when you do that, so you will get the value for the R. So that will going to be something, just calculate it. Okay, and then put it here. The G is going to be 6.67 exponent negative 11, and yes, omega was 4.97 exponent negative 4, I think, or negative. -8.
-8, yeah.
Yes, what's the value? Is how much? Ajay,
I'm
by the
getting
way,
one
wait, wait,
point.
wait, wait. Did you square that and did you group that?
Yeah,
If you do,
I'm
then
getting
mm-hmm.
1.148 into 10 to the power 20.
20. This is cubed, by the way. Wait,
I think there's another way to solve this, even if we take capital M A and M B.
Ajay, wait, 8 seconds. MB is a mass. Okay. MB is this mass. Okay. And they're moving from the common center. Um, no, we have to take the whole distance for while we are talking about the common center. Wait, if I just replace that with R, and this is also, oh, sorry, this one, and this is R, and if R is the whole distance, let's say, and it is 2.8 exponent 11, okay, because we have to convert that into kilometers, okay. Now, so now just try to find out. Let me see. So 2.8 exponent 11 cubed into 4.97 exponent negative 8 squared divided by 6.67 exponent negative 11. Okay, I'm getting mhm. For the gravitational force, the distance is going to be the center to center, and for the centripetal force, that is, oh my God. For the gravitational force, the distance is going to be center to center, and for the centripetal force, the distance is going to be d minus the whole thing, 2.8 exponent 11 minus the d, minus d. Okay, and then omega squared. So, and since this is only for A, so for A we just need to put D, not the whole thing. Okay, so
D is 7 into 10 to the
yes,
power
yes, yes,
7, right?
yes. So this is R square and that is D. Okay. Now if we just so D is going to be 7.7 exponent 7. You can take 10 because it is like in kilometer. Okay. So and omega is 4.97 exponent negative 8, okay, and then divided by, okay, then you have to multiply the r with its value, okay. and R is the center to center separation, which is 2.8 exponent negative exponent 11. Okay, because the whole distance is 8, and then it is kilometer in kilometers. So you have to convert it and then divide it by g, which is 6.67 exponent negative 11. Okay.
I'm getting 2.72 into 10 to the power 29.
Okay, 2.7 exponent 30. So fine.
The thing is, I didn't use this method. The last question, they gave
Mm-hmm.
a ratio, so I just used the
Yes,
ratio.
you can do that.
Yeah, and I got this
Okay,
answer.
but which thing you equate the ratio with?
Uh, I just found I just found the mass of Ma. Like, uh, we cancelled out Mb and found mass Ma,
Mm-hmm.
and then I use the
Like
ratio.
then how you did find out, how did you find out the mass of Ma then? Using mr omega square or what?
Uh, Gm Gm Gma over
Mm-hmm.
r squared is equals to mr omega squared
Mm-hmm.
is equals to r omega squared. Sorry, after you
Okay.
cancel Mb, then when you bring r squared to the other side, it becomes r cubed omega squared,
Okay.
and then
Okay,
Ma
fine,
is
fine.
equals to r cubed omega squared over g, which is
G,
6.67
and then you multiply
into.
3 at the end,
No,
or
you have to
divide,
divide by
yeah,
3.
divide everything.
Yeah,
Okay, fine, no problem. Okay, now
it's
let's.
correct.
Yeah, yeah.
Okay, okay.
By the way, the actual mass is 2. It's just 2 3 exponent 10 into 4.97 exponent negative 8. Let me see if I'm getting the value, and then 2.8 exponent 11 squared. Okay, squared. Okay, omega is also squared. Omega is also squared, and we have 6.67 exponent negative 11. What? 2.8 exponent 11. Okay. I am getting 2.0 exponent 29. Are you getting 30?
For what? No, I'm getting 2.7 into 10 to the power 29.
Okay. The marking key says it is 2.0 exponent 29.
Yeah, that's what I'm getting. Oh, 2.0.
2.0,
I don't,
yes. Um,
I don't know.
and I think you're just making the mistake in this portion where you take R and R the same, right? Like where you did GMA over R square is equals to R omega is square. Okay, so these two are different. Okay, because in the GM formula, this I is going to be the center to center separation. Okay, and this I is going to be the center to center between the stars. Okay, and this I is going to be the point of the rotation till one star. Okay, so that's why it will going to be different, right?
Oh, but the thing is, the difference is like very small, so it's
Yes.
like the difference in the values. Yeah.
Yeah, no, um, but actually, the concept is wrong because they won't give you mark if you use these two distances as the same thing. Okay.
What then we have to mark it like differently, you know, because I saw you're using the r squared, so I thought it was the same thing, like the
No,
same
I
distance.
have to change this thing as well. Okay. So this x square is it should be L. Okay. Look, this should be L. Okay. So for one star, The center to center distance is going to be L, right? So this is L. And for the other mass, if you're talking about M2, so M2, for M2, you have to do,
Should just be X.
for M2, it's L minus X, okay?
Oh, okay.
L minus the X and then omega squared, right? And then the M and M2 goes off. You'll be left with M1 and over L squared and then L minus X squared, okay? Now that's it. Clear?
Yeah.
Okay, so that's done. Okay, please move on to the next question.
A satellite is in circular orbit
Just
above
ignore it.
Mars.
Wait. Let me just say, let me just ignore this question by pasting the thing. Paste. This is nothing, by the way. It's actually a part of the other question, which we're not doing. Okay. Okay, fine. Okay, the gravitational force, you know that it is a gravitational force, basically the um. Okay, this is a force, by the way. So you can explain that. Do you remember the definition, by the way?
Is this it's gravitational force, not like potential or
Yeah,
field strength.
it is basically the
Mm,
um gravitational force, the force acting between the two objects. Okay, between the two objects due to their masses. Okay. So this is the concept of the gravitational force, right? Now, please move on.
A binary star system consists of two stars S1 and S2, in each in a circular orbit. The orbit of each star in a system has a period of rotation T. Observation of the binary stars from Earth are represented in Figure 1.1.
Okay. So at time t equals to 0, then t equals to t over 4, like quarter time, then half time, then three quarter, and then four quarter. Okay.
Observed from Earth, the angular separation of the centers S1 and S2 is 1.2 into 10 to the power negative 5 radian.
Mhm.
The distance of the binary star system from Earth is 1.5 into 10 to the power 17 meters. Show that the separation d of the center S1 and S2 is 1.8 into 10 to the power 12 meters.
Okay. So if we try to imagine, um, they're saying observe from the Earth's angular separation. Okay. So let's say the Earth is right here. Okay. And they're saying observe from the Earth. Okay. So the angular separation of the center of S1 and the center of S2 is in radian. Okay. So, um, okay. So this and this. Okay. Right. And this distance is given, right? Because it is in radian. Okay. It is in radian. Okay. And how much? 1.2 exponent negative 5. Okay. So 1.2 exponent negative 5. So this radian is given. Okay, this angular separation is given. Now they are asking, show that the separation d of the center of S1 and S2 is given. So, okay, so basically they're asking you this distance. Okay, and you can see that it is like the circular arc. You can use S equals to r theta, right? But we know that the S equals to r theta thing is only applicable where S is going to be the arc length. Okay. But for this one, since the angle is very small, so the arc length is going to be like this straight line. Okay. So that's why. Clear? So
So we can't use that.
we can use that s equals to r theta, right? Because of the angle is very small, that's why. Okay, we can use it. So the r is going to be show that the center, okay, the okay 1.5 exponent 7 is this distance, 1.5 exponent 17 is this distance, okay, the radius, right? So 1.5 exponent 17 times the radius, which is 1.2 exponent negative 5, 1.2 exponent negative 5. Okay, how much?
Uh,
Yes,
1.8 into 10 to the power 12.
1.8. Okay, 1.8 exponent 12. Exponent
This
12.
is meters, right?
Yep. Okay, let's move on.
The stars S1 and S2 rotate with the same angular velocity omega about a point P, as illustrated in figure 1.2. Point
Okay.
P is at a
Hmm.
distance x from the center of the star S1. The period of rotation of the star is 44.2 years.
Okay.
Calculate angular velocity,
So omega is equals to 2 pi
2
over
pi over
t,
t,
right? And t is going to be 44 years, and just convert the year into seconds. 44.2
44
into 365
times.
into 24 into 60 into 60. Oh, how much?
4.51 into 10 to the power minus 9.
-9. Okay, let's move on.
But I think we can just take it 4.5 because the previous answer is in
They're
one
in
decimal place only.
3SF. 3SF. So we have to take it as 3SF. Okay. We have considered 3SF, the significant figure, not the decimal places.
Oh, okay, fine.
Okay. And you can also check out the other values as well. This is 2SF, 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 and any other
It depends
value?
on each question, like
Yes,
the.
yes. For A2, it
Okay,
depends
okay.
on each question. You have to consider whether you have to take it in 2SF or 3SF. Okay. So more data is in 2SF, just keep it in 3SF, no problem. Okay. Move on.
By considering the forces acting on two stars, show that the ratio of the masses of the stars is given by mass of S1 over mass of S2 is equals to D minus X over X.
Okay. So since they're saying by considering the forces, okay.
So
Uh,
the force due to
yes.
Fg is equals to mr omega squared.
No, the forces due to on the two stars. So basically, the force will going to be the same, right?
So just Fg is equals to gmm over r square.
Or just relate the two centripetal force. Okay. You can say that the centripetal force, centripetal force, okay, about this point P, about point P is same, right? So for both the stars, so we can take centripetal m of S1 Okay, and then R, the separation is X. Okay, for S1 it is X, and then omega square is equals to M of S2, and then its distance going to be a D minus X. Okay, so D minus X and then omega square, right? Cancel this out, and you'll be left with M of S1 over M of S2, okay, is equals to uh, D minus X divided by X. Okay, clear? You
Yeah.
can, we are using this concept, okay? This one. When you have two stars, so you relate the two stars with their centripetal forces, okay? Okay, let's move
Okay, okay.
on. Okay, please move on to this one.
The mass M1 of star S1 is given by the separation GM1 is equals to D square into D minus X omega squared into omega squared, where G is gravitational constant. The ratio in 2 is found to be 1.5. The previous question.
Yes, related to the previous question.
Okay, then use data from B and your answer in CI to determine mass M1.
Okay, so we know that S1 over S2, the masses, okay, is 1.5. Okay, so and we can use this equation to find M1. Okay, so M1 is equals to the whole D was what was okay, so 1.8 exponent 12. Okay, 1.8 exponent 12. Okay, and then D minus X. So again, 1.8 exponent 12 minus X. X is going to be one of the things S1 till the center. Okay, what will be the X?
The radius? Not the
No,
radius,
it's
sorry.
not the radius. It is basically this distance from S1 till the center. Okay, do we know it? The distance of the binary star system to Earth. Okay, not given, and
What about the arc?
the arc is 1.8 exponent 8. So it's basically the distance between the two stars, huh? And the P lies here. P lies here, somewhere here, let's say, or basically it is next to P, S, this one. Okay, so ha ha ha. X. Okay, so we should use this relation to find X. Fine. Okay, let me see. X and then omega squared. Omega was 4.51 exponent 9. Okay, negative 9. Okay, now and divided by G, which is 6.67 exponent negative 11. Okay, 6.67 exponent negative 11. Right, now we basically have to do, just bring it down and this whole thing down. Okay, so they mentioned that 1.5 is for this one and that one, right? So M of M1 over M2 is 1.5, and also D minus X over X is 1.5, right? Clear? Yes. So we can use this relation to find X, okay? So D minus X is equal to X over X is equals to 1.5. Okay, so 1.5 to 2.5, so D is equals to 2.5X. Okay, and then 1.8, come on, 1.8 exponent 11 divided by 2.5 gives you the x. Okay, just find that out.
7.2 into 10 to the power 10.
Okay, and you can put it here. Okay, 7.2 exponent 10. Actually, by the way, did you put this square right here? And this is also squared. Mm, d minus x. So 2.5 divided by d.
I'm getting a 1.7. Uh, yeah, 1.7 into 10 to the power 30.
1.7. Okay, exponentially. Fine. So these are the two questions for the binary stars. Okay. Now I'm ending the class right here. And I also share the questions with you. So just try that at home, and we'll do some of the remaining chapter. We'll do the remaining chapter of this gravitational potential in the next class. Okay. Okay, that's it.
Okay. Sir,
Mm-hmm.
this